In this video, let's look at this analog devices tutorial MT001, and it's about signal noise ratio of ADC system. And you probably know this formula somewhere. So this video, let's talk about where this come from and how can we derive this mathematically. And when you digitize analog signal into a digital output, you always get some quantization noise or quantization error. Sometimes we call this a sampler error or sampler noise. What happens in an analog signal, if you have an analog input here, in an analog signal is it's always in a continuous domain. And when you digitize, you turn the analog signal into this digital output. It's basically small steps. Okay, and for a given analog input signal, for example, here, and once you digitize, it's some number. You will always get this number or either this number or that numbers, but the actual analog input could be falling in between these two numbers, anywhere in between. So that means in statistically, you always have an error of plus minus half Q, where the Q is a small steps, basically a small step in the system. And if we have a say 10 bits ADC, and with a reference signal 5 volts, so what's the Q? The Q, the small step, is 5 volts over 2 to the power 10. And we are just assume we connect the system into a basic single added ADC input. And if what is error due to this quantization problem here, and if we plot here, if you use error, it's the input signal, which is the analog signal in a continuous domain, it's a straight line in this case, and we subtract the output, it's tiny steps. So what you left over is very similar to a triangular wave, a series of triangular wave. Okay, and the height, the peak-to-peak value here is basically the peak value from here to here. That's 1 LSB. That's 1 Q, 1 least significant bit. Okay, and what we really want to know is the RMS value of this error, the triangular wave, because RMS value, the square of RMS value basically is the power has been imposed by this noise system. Okay, and how do we evaluate or calculate RMS values? There's many ways, and here this technical note shows a very simple way. So I just copy this plot out so we can work out this equation. What we want to know is RMS value of this triangular wave, and if we just look one period from here to here, and we know this line ET assumes ST, so it's a linear equation with the slope S, and this is time. And we know the peak-to-peak value is Q, so from here to here is Q over 2, and the negative side is minus Q over 2. And so what is the time step here? What's the time step here? Because that's where easy is Q over 2 equal to ST, so we know T equals Q over 2S. Okay, so that means the time step here is Q over 2S, and this was minus Q over 2S. Okay. With all the information here, so what we really want to know is RMS value of this triangular wave. We have talked about this before. RMS value, we call that ERMS. We can take the square of the RMS value, basically have the unit of power. And by definition, we will take the squared first, that's ET squared, and we take the sum. And then we take one period, so it's 1 integration 1 over Q to S, from Q to S, from here to here, and a dt, and 1 over t. So that's the mean We don't take the square roots any square root here because we have the square that canceled. Okay, now let's work this out. So what is the t? The period of t is from here to here. That's basically from minus q to s over to q to s. So the capital T, the period is q over s. And 1 over t is the invert of that. So it's s over q. So the integration is right here, q over 2s, q over 2s. Et is st, so squared s squared t squared dt. And the s squared is a constant. We can take the s squared out of the integration and combine with this s, we got s cubed over q. And minus q to s over q to s. And t squared dt. So s cubed over q, t squared dt is 1/3 t cubed. The range is q over 2s minus q over 2s. Okay, and keep working on. So we have just clean up here. S cubed 3q and q over 2s cube minus q 2s cube. Okay, and this is a odd function, so we can take the next side out and turn this into a positive size. So this essentially is 2 times this term. Okay, so it will be s cube 3q and 2 times q over 2s cube. So s cube over 3q, 2 times that is q cube times 2 here is 2 to cube is 8s cube. Okay, let's clean up here. We just cancel that. So it's 2 cancel here is 4, and the q have cancel here, leftovers q squared. So it's basically leftovers q squared 3 times 4 equal to 12. Okay, and now we know the RMS value of this triangular wave is E RMS value squared is over q over 12. Okay, so that's if we take the RMS values, the squared RMS values q over 12, and we back to here, RMS quantization noise, the square roots of that is q over square roots 12. Okay, so this is very important or very famous equations, because once you know the RMS value and you know the square RMS value, basically is the variance of the signal. The variance of signal is squared RMS value is q over 12. So this is a total variance, so a total and possible energy for this due to this ADC quantization noise. Okay, this noise will distribute over the whole Nyquist frequency. Okay, because this is a constant. Once the ADC system decide, the Q is decide, 12 is a constant. So this quantization variance, or the total quantization power, is a constant for a given system. However, this noise will distribute over the whole Nyquist frequency of your system. That means if you sample the ADC faster, okay, higher sampling rate, so higher Nyquist frequency, and your power density is basically this number divided by the Nyquist frequency, right? If you have a higher Nyquist frequency or higher sampling rate, so your overall quantization noise will be lower. So this is basically the benefits of the oversampling. Okay, now let's work out the this signal noise ratio. Let's assume we have an input full scale sine wave, okay, and like that. So remember where this come from is if we have a sine wave and we know the q Q equals to the full scale. Let's see. The reference signal, let's say call that full scale, divide by power to 2. Okay, the full scale value, or the peak to peak of the full scale value is VFS equal Q times 2 to power n. So that's Q by 2 times power n. And but in the sine wave decide we have the this amplitude is half the peak to peak value, so just divide by 2. Okay. So. And because it's a sine wave, we know what's a sine wave. If you know the amplitude of sine wave is Q power 2n divided by 2, then RMS value of that is basically divided by square root of 2. Okay, I have a video about how to get the RMS value of sine wave. So that's when you have here, it's the input signal, that's the RMS value of full scale input signals. And by definition, remember the signal noise ratio definition for n bits converter is like this. Signal noise ratio equals 20 times the log, the RMS value of full scale input divided by the RMS value of the quantization noise. Okay, remember the RMS value is always calculated with the signal noise ratio is always calculated with the interim RMS value, because that's RMS value basically has the meaning of the power. And then we can get these two numbers into the system. That will be straightforward. I think that's RMS value is Q 2n 2 squared 2. And you divide by the RMS value of that. That's, remember, it's Q over square root 12. And they can invert this, this is square root 12 divided by Q, so the Q and Q canceled. And you can work out the math here as Q and Q cancel. Eventually you get this equation. Okay, it's two log numbers, and then you can combine them eventually to here. Look here, it's over, this is for the bandwidth is over from the DC to FS, the sampling rate divided by 2. That's basically from the DC to the Nyquist frequency. And by looking at this equation, you notice the signal noise ratio is proportional basic to the bits of the system. So if a 10 bits or 12 bit system will have much higher signal noise ratio than the 10 bits, and so on. And also the signal noise ratio is independent of the actual bit size. Okay, so and this technical notes is also talk about the what's the signal noise ratio for a oversampling system when you have a higher bandwidth, and also a lot of other stuffs. But I think you can look at that. I think the core of this technical notes is the first part. Hopefully this help you. Thank you.